Let's back out and look at the big picture. Here we can see nearly the entire Gulf of Mexico and most of the southern half of the United States. Now, of course, what we're interested in is the beautifully colored portion of this image. It sure is intriguing, and look how big it is. The full width of the colored region is about 550 miles or 885 kilometers. If we take this feature and overlay it onto the North Sea, we get another perspective on just how large it is. Surprisingly enough, we're going to see how cooking pancakes, the Grand Teton Mountains of Wyoming, and beautiful Badlands all give us critical insight into this amazing geologic feature. Hello, I'm Myron Cook. I'm sure excited to go on this journey of discovery with you because we're going to learn about some of the most fascinating and spectacular geology on the planet. And to think that the vast majority of you have never even heard of it. I want to start by better understanding the beautiful map that I've shown you. So what kind of map is this? Well, it's a bathymetry map, or a water depth map that has been colored according to the depth of the water. I then overlaid this bathymetry map on Google Earth imagery so as to give us better spatial context. Let's focus on the color scale to help us understand this map better. At the top of the scale is a light pink color, and that corresponds to 150 feet of water depth. Whereas when you get into kind of the brick colors, we have the 3,500 feet of water depth, and so on down to where you get at the bottom of the scale. In the green colors, the dark green colors, you have 8,000 feet of water depth. Now to the south of this feature, in the dark blues, the water depth ranges from 10 to 12,000 feet. The southern margin along this region is referred to as the Sigsbee Escarpment. So simply put, this map is showing us the topography or the terrain of the ocean floor. So with this understanding, the real fun begins, and that is making observations. What can we see here? I'll tell you what, this looks otherworldly to me. There are so many features that we can see here that we could discuss, but I want to start with one that's fairly obvious, and we'll go from there. Can you see all the craters in here? I mean, it's just full of craters. They remind me of this beautiful meteor impact crater in Arizona. The landmark, in fact, is named Meteor Crater. It is about 7/10 of a mile across and 550 feet deep or so. This is a higher resolution version of the bathymetry map where we can see more details. Let's take a look at this beautiful, relatively small crater that I've highlighted. It is 6.3 miles wide, which is 10 times wider than Meteor Crater in Arizona, and it's about 750 feet deep. The somewhat oblong crater next to it is about 1,700 feet deep. As we look at the bathymetry map, we see many of these crater-shaped depressions, don't we? And that means that any theory that we develop has to explain this abundant number of them. Of course, we do know that asteroids and comets can break up. So in theory, you could have many large chunks of these bodies coming in and creating many craters. However, there's something else that we have to explain. As you notice when you look at this map, you'll see that not all the craters are round. Some of them have elongated or irregular shapes. So we have to be able to explain those too. And so our journey continues, trying to discover what it could be, but we have to be open to impact craters at this point. Something we can do that is very helpful is look deep into the earth and see the geology underground. It turns out that we can generate sound or seismic waves that penetrate the earth and then are reflected back off of rock layers or strata back to detectors, and then processed in computers to give us a seismic image. It is the same technology we use to create sonograms in the medical industry. Let's take a look at one of these seismic images that is some 65 miles long along this black line that I've drawn on the screen. This image will cross two crater-like depressions here, and then go off into the deep water out here. And here is this beautiful seismic image. We are looking at a cross-sectional or sideways view. At the top in blue, it represents water. I've just colored it in as water. And on the left, which is to the north, we see the two crater-like depressions here and here. And then to the right, which is south, we see where the water becomes a lot deeper and you come off the front of the Sigsbee Escarpment. Let's focus our attention for a minute on the far right side of this image. See all the layering in here, the lines in here? Those are rock, thick rock layers, underground of course. And the orange color that you see is just highlighted orange when you have a strong amplitude or a strong strength in the reflection. That's all that orange is. Now, moving over to the left, you see all the pink area that's colored. That's something that I put in, that I interpreted this seismic line. So I colored certain areas pink. So why did I color these areas pink? Well, what we do when we look at seismic, we look for one thing that we do, of many, many things, is we look for what are called seismic facies, or basically how the seismic looks, the character it has, and we call it a seismic facies. And it turns out in this pink area, you really don't see any layering in there, do you? If you look, you see some noise in there, but you don't see the nice layers, the lines that we see elsewhere. So that is a particular seismic facies. And it turns out that this pink that I've highlighted is the entire key to what's going on here in the Gulf of Mexico. Let's move on to some other observations and we'll come back to this image. Well, believe it or not, cooking pancakes, something that most everybody does, gives us an important clue about what's going on out here in the Gulf of Mexico. So I want to cook a pancake here, and let's make some observations, should we? I'll get some batter here and do my thing. Okay, I think I'll make it a little bit kind of oblong, because that's what we see out there on the Sigsbee, don't we? I'll make it a little oblong. Okay. And cook up this beautiful pancake. And I want you to make these observations here and see if you get the clues that I want you to get. There's some nice bubbles building up here, I see. Well, it turns out bubbles aren't the clue. But we do see some interesting edges on here. Nice little edges. Oh, that looks pretty good, actually. Not the best at this. Okay, so what do we see? Let me grab this. And we can see some rounded lobes, can't we? I think you'll agree that along the Sigsbee Escarpment, we see similar lobe shapes. Using Google Earth and their bathymetry data, we get a very nice 3D perspective of this Sigsbee Escarpment. It kind of reminds you of a giant pancake, doesn't it? And I do mean giant, because the front of this escarpment in this region is 3,000 to 4,000 feet high. Wow. We see these rounded lobe fronts. So what caused that? It came from something that flows, a viscous or thick material that flows, like cement, like honey, and other things. So that is a really important clue. Well, you're thinking to yourself, what in nature flows? Well, the obvious one are volcanic lava flows, right? Okay. What about mud flows? Those big debris flows, mud flows that you've seen. Yeah, they can have this lobe-looking front. So that's an interesting one. Another one is ice, glaciers. Well, yeah, in fact, glaciers flow, don't they? In the end, the only way to know for sure what's going on is to drill a hole. Drill a hole down into this and bring up a core sample, which is a continuous cylinder of rock. And that's been done many times, where you take a drill bit and a special drill bit, and you can cut a continuous cylinder of rock. Let's see what that looks like, and that will tell us absolutely what it is. And here is that core. Now, some of you still may not be sure of what type of rock you're looking at here. Let me give you a clue. You use it every day in your food. Yes, it's salt. Wow, that's rather unbelievable, but it is salt. Now that we know it's salt, you're probably thinking to yourself, wow, I didn't know salt could flow, that it could flow like a lava flow. And in fact, it can, and it does under certain circumstances, and we'll be talking about that a bit more later. But for the moment, I want to discuss about the volume of the salt. Now, think about this giant bathymetry map that we've been looking at, how huge of an area that covers, how much salt this must be. And we still haven't talked about the thickness of the salt. So the next thing I want to do is look at the seismic line again, and let's see if we can figure out just how thick this salt is. This is the same seismic image we saw earlier. As you'll recall, it's 65 miles long, so it's a long way across there. And now we know what the pink area is that I colored in. It's salt. The beautiful and spectacular Teton Mountains of Wyoming. I was there a couple of weeks ago, and I had a flash of inspiration as to how I could use these mountains to help us understand the immensity of the salt deposit that we've been studying. So I took this photograph. Now, what I'd like you to do is, in your imagination, think about how big would these mountains be if we placed them right in the seismic image? Do you have a wild guess? Okay, let me draw a sketch of the Tetons in here for you. It's hard to believe. Man, it's that tiny little sketch I put in there representing the Teton Mountains. That means that salt body is some 14,000 feet thick. And that body that I sketched that in is actually what causes the flow appearance. That's what flowed out, is that particular body of salt. Wow. I had the great fortune of studying the geology of the Gulf of Mexico for 3 years. In fact, I had the amazing opportunity to geologically interpret these seismic lines, some 80,000 miles of it across the Gulf. And let me tell you, the geology that I saw was rather overwhelming. I just couldn't get my head around how spectacular the geology was down in the Gulf of Mexico. Wow, well, how do you get thick amounts of salt? Well, first of all, let's talk about where the salt comes from. We all know seawater has salt in it. Okay, it's about 3.5% by weight salt. So what that means, let me get a little prop for us. That means if I take this pan here that's, well, it's about 5 inches, well, 6 inches is just a little more, 6-inch pan of water, okay, and of seawater, I should say, and we boil it right away, just boil it till there's no water left, we would have 1/10 of an inch of salt. Okay, so that means for 1,000 feet of seawater, if we were to boil 1,000 feet of seawater, we would have about 17 feet of salt. Boy, this is going to take a long time. This is pretty hard to get to thousands of feet, right? An important number of thickness of salt that I'll come back to is 4,000 feet. So 4,000 feet of salt, to get that, you would have to evaporate 45 miles of seawater. So it's kind of, well, how does that happen? Or is there some other way we get all this salt? Well, no, it does come from seawater under certain special conditions. It seems that always occurs in geology. Let me get a map for us. And here is this Blakey map, this deep time map. For reference here's an outline of part of Texas. You see the early state of Florida here. This is Africa region here, and down in here is South America. This was all together as the supercontinent Pangea, and about 170 million years ago it started to break up and move, and all these continents started to go to where they are today. So we started opening up here and breaking this apart. Now what this means is we have a restricted seaway. When we break things apart like this, we call it rifting, okay? And we have a restricted seaway that comes in here into the Gulf of Mexico. When it's that restricted, when you have just the right conditions, you have evaporation of the seawater, and you have just enough come in to replenish it, but it maintained very high salinities. You need to have a saturation about 10 times of the seawater we have today. So if you evaporate it enough water to get that 10 times, it starts to precipitate salt and it drops to the bottom of the seafloor, okay? And so you start building up salt here because you have this really nice condition. And with deep time, it doesn't, for a geologist, it doesn't take that much time, but with 1,000,000 years, for instance, if you have the right condition in here for 1,000,000 years and you're precipitating salt, you only have to evaporate 3 inches of seawater a year. And lo and behold, you can deposit a very thick body of salt in the early Gulf of Mexico. Well, we still don't know how these craters or depressions that we saw earlier in the presentation formed, do we? Or how this giant salt tongue or canopy of salt formed to give us this flow look to it, how it flowed out. So let's get into that discussion. I want to start with this cross section here, a sketch. Let's focus over here on the right side. This represents the body of salt that was deposited in the bottom of the Gulf of Mexico. And it got up the original salted deposit. And the maximum thickness of that body was about 4,000 feet thick right here, okay? And remember, that's about 45 miles of seawater to evaporate to get that kind of thickness, okay? So we have this mother salt, the original. Now I want to take and look closer in. And this is where we'll focus right here. And at this moment, the salt is deposited. There's still seawater here on top of the salt. It's very saturated with salt. And then through time, sediments start to come in over the top of this salt. Let me just draw a line of sediment, okay? Maybe two close together ones, okay? And after a period, not much time, you start loading the salt with sediment on top, and salt is very weak. And you can get a little depression in the salt. So let me put a little depression right here, okay? And with this depression here, then the sediments on top kind of sag in, but you're creating a hole, and it starts filling in. And it starts and pushing the salt because it's so weak. It loads that salt. And that salt has to escape somewhere. And so it starts flowing out away from this area, right? Because you're pushing the salt out or loading it, and it's flowing out. And so it needs a place to escape. So let me put a fracture, let's call it, it can be fractures, lines, or like chimneys. I'm going to actually put a chimney here. Okay. And salt comes up this chimney and kind of stays here, pretty close to the surface of the sediment. The sediment's still coming in through time. We load more sediment on it, okay? And more. And while that's occurring, this chimney of salt, so to speak, it's fairly round. They can be. This one I'm sketching is. It kind of stays up close to the surface of the sediment. And it just keeps going and going. And that's where this salt goes. There could be many of these chimneys and or walls, okay? And as you keep depressing this and loading this salt, it just keeps going down and filling in what we call a mini basin. Let's go to another phase in this. Going through time, this keeps going down and down and sagging down. It can go all the way down, clear to the bottom of the salt. It can't go further than that because then it hits a strong bottom and it won't, there's no salt. Okay, and this salt continues to move away from here. It goes way down. And as it's going down, these sediment layers in here, it's just filling in with sediment, like this. They keep sagging in, filling in with sediment, depressing in. And that is the mini basin. And that's what forms these craters in irregular shapes, are these basins that form. If we look at the seismic again, we'll recall this. Here we see two mini basins, and they're very similar to what I showed you on the sketch. You can see the layers as they're filling in the basin, can't you? The mother salt, or the original layer of salt, was approximately between these two dashed lines. There isn't much of the mother salt left because it has all moved into salt walls, diapirs, and canopies or tongues of salt. We say that it has been deflated. So continuing through time, you keep building and sagging in until you run out of salt here in this mini basin. It bottoms out. You can also have what are called diapirs. This chimney at some point can develop a big bulb of salt, like a diapir we call them, okay? So those are the basic principles involved to create all these depressions and these mini basins. So now on to this giant flow of salt that we've seen, this salt canopy. How did that happen? First thing I want you to know is the Gulf of Mexico is already half full of sediment, approximately half full of sediment. So as it opened up and the Rocky Mountains eroded and everything coming down in, it started filling in the Gulf of Mexico, all this sediment from the various rivers, ancient rivers and modern rivers. So that's an amazing thing right there. And that is the key to this salt canopy. And that's why I showed you an image of the Badlands, a little short video clip of these beautiful Badlands, because so much material has been eroded away from the west down into the Mississippi River Valley and other rivers too as you go further south and heading to the Gulf of Mexico. And with this huge sediment influx, you're bringing it in and loading this salt very rapidly. And also it happens that you're bringing it out onto the thickest part of the salt, this mother salt we call it. So the sediment loads this salt, this mother salt, or a fancy word we use is autochthonous salt, meaning it hasn't moved. So it loads it down very rapidly. Let me sketch that. It is just filling in very rapidly, okay? Filling in. So as we rapidly load, of course, this salt wants to get out of the way, as we've mentioned before, and now it develops kind of more like a fracture kind of system, or multiple ones, and creating walls, okay? Walls of salt as it breaks free after it's been loaded, not a whole lot, okay? And then as you load this, and it's the thickest area, and you have all this salt volume that's coming this way, feeding in to this direction, it breaks free and puts out a very large salt body. Right out onto the seafloor, right like this, okay? Now what I want to point out is that this is not to scale. Remember, this mother salt, or this autochthonous salt as we call it, meaning it has not moved, is some 4,000 feet thick in its thickest area. And this body of salt, this giant canopy in its thickest part, is 14,000 feet. So if I were to draw this to scale, I'd have to make this canopy way thicker, right? This is just to help us understand the concepts involved, not necessarily the scale. So of course, as the salt flowed out, you still have sedimentation going on, and you're covering this salt canopy and on out to the front, just like we see in the seismic. So on the seismic, we see the mother salt here at the base with the arrows pointing to the motion of the salt. It comes up this giant salt wall, comes out onto the surface and flows in this great canopy of salt. And after this, sedimentation continues to occur. And so we have accumulated all this sediment in this area on top of the salt. There's so much wonderful geology out in the Gulf. I could go on for days talking about it. But we have to end it here, and I sure thank you for watching the video, and I hope you enjoyed it.